Alright, so section 7.8 we have finished in the last lecture. So I'm going to start the section 7.9. So an extension f over k is said to be simple extension if f can be obtained by adjoining an element to k. So f is k theta for some theta in f. In this case, means when f equals k theta, theta is said to be a primitive element of f. So naturally this theta is not unique. You will get many elements in f by which you will get f on adjoining to k. Alright, so this first theorem will give an equivalent condition to determine the extension is simple. So let's say f over k be a finite extension. So I hope you know about the in-house exams. That will be online, right?
Yes, sir.
And classes will start from offline classes will start from 25th onwards, right? So final exams will be in offline mode. ठीक है? So f over k be a finite extension, then so I hope I mean many of you are happy with this
Yes, sir.
because that was one of your many of you were asking, right? So it's good to see back to campus. So then f is simple extension, that means f is k theta for some theta in f. If and only if there are only finitely many extensions of or finitely many subfields of f containing k. All right. So first, suppose that extension is simple. That means f is k theta for some theta in f. What I want to show that there are only finitely many subfields of f containing k. That means there are only finitely many subfields in between f and k. All right. So let's say E be a subfield in between of f containing k. So, and remember, we are working over a finite extension. It is one of the condition. That extension is finite. So means algebraic. So algebraic है, so that means we can talk about the MMP of this theta over E as well as over K. So that's what I'm going to do. So let's say fx with the MMP of theta over K, minimal monic polynomial. And gx be the MMP of theta over E. So gx will divide fx because gx and fx both are polynomials over E, and gx is the least degree polynomial. So then gx will divide fx, and this division takes place in ex. All right. So let's say what you want to call maybe gx. Suppose it is a0, a1x, m minus 1 x m minus 1 plus minimal monic polynomial, so leading coefficient must be 1. So this is, suppose it is this, and it's a polynomial in ex. ex के ऊपर माना हुआ है, right? So this is in ex. So that means coefficients are coming from e. What you do, collect all these coefficients a0, a1, am minus 1, adjoin all these to k. Put e dash to be k, and then adjoin the coefficients a0, a1 up to am minus 1. तो ये कहाँ होगा, किस किस के बीच में होगा e dash? ये coefficients आ रहे हैं e से, right? So all these ai's are in inside e, k already contained in e. तो ये e dash will be contained in e containing k. So then e dash is a subfield of E containing K, and the point is, can I say that कि जो GX है it is still MMP over E dash 2. देखो GX MMP था, let me go back to you. MMP है E के ऊपर, MMP है थीटा का E के ऊपर. अब इस MMP के जितने भी कॉफिशिएंट थे वो सारे E डैश में हैं. तो कैन आई से कि ये जो, तो दैट मीन GX दिस, ये जो MMP E के ऊपर है, दिस MMP you can treat it as a polynomial over E dash 2 because all the coefficients of GX are in E dash. So can I say that this theta is still MMP, sorry, G in this GX is MMP of theta over E dash 2? Because the point is suppose नहीं है, so that means you must have another polynomial over E dash of degree strictly less than degree of gx satisfied by theta, but E dash is contained in E, तो वो polynomial तो E के ऊपर भी है, that will violate the minimality of gx over E. Is that fine?
Yes, sir.
So and gx is the MMP of theta over E dash 2. So basically what is happening, you have K contained in E dash. E dash कहाँ है? E के अंदर. And where is E? F. And what is F? F is what? F is K theta. F is K theta. So that means F, which is K theta, E dash theta, E theta. Is that fine or not? क्योंकि ये E dash theta, E theta, ये दोनों F के बराबर होंगे. नहीं, कुछ कंफ्यूजन है? भाई K किसके अंदर है? E dash के अंदर. K theta किसके अंदर होगा? E dash theta के अंदर. What is K theta? K theta is F. F is contained in E dash theta. और रिवर्स इंक्लूजन आपके पास है ही ऑलरेडी. E dash कहाँ है, किसके अंदर है? F के अंदर. थीटा कहाँ है? F के अंदर. You will have exactly the same logic will be applicable to E theta. Is that fine?
Yes, sir.
Okay. So that means you have the equality. So that means the degree of F over E dash, this is same as the degree of MMP of theta over E dash. This is same as degree of MMP of theta over E dash. And क्योंकि MMP तो GX ही है, That means this is same as the uh, degree of f over e2, क्योंकि gx e के ऊपर भी mmp है और e डैश के ऊपर भी. Is this all right? ये तो सेकंड चैप्टर सेकंड सेक्शन में एक रिजल्ट था ना, डिग्री ऑफ k थीटा ओवर k इज द mmp ऑफ थीटा ओवर k. तो ये f क्या है, e डैश थीटा है. f is e dash theta. So degree of e dash theta over e dash is the degree of mmp of theta over e dash. वो mmp gx है. And exactly the same logic will be applicable to degree of f over e. So you have the equality. All right. So go back. आपके पास you have this tower of extensions, right? And what is happening? This degree is same as this degree. What's the conclusion then? Yes, simple. E dash is equal to E because F over E dash, this is same as F over E into E over E dash. और finite extension आपको दे रखा है, so all these extensions are finite extension. So we have that means E equals E dash. Now let me recall you what we have done so far. We assume that the extension is simple extension, that means generated by one element, so that is f equals k theta. So what we are looking for, we want to show that there are only finitely many subfields in between f and k. So we consider arbitrary subfield e in between f and k, right? तो ये जो arbitrary subfield है, finally what we have proved कि E can be obtained by adjoining all the coefficients of mmp of theta over E 2k. Is that fine? That is, E can be obtained by adjoining all the coefficients भाई E dash क्या था? I hope you are able to recall what is E dash. E dash is k a0 a1 a2 a m minus 1 और ये ai's क्या थे? coefficients थे gx के. Coefficients of mmp of theta over E, that is वो gx है. और ये gx क्या है? I mean gx is a factor of fx, monic factor of fx. Is that fine? भाई देखो, somewhere we have written gx divides fx, right? So we started with a field in between, and then we have proved that that field can be obtained by adjoining the coefficients of some monic factor of fx to k. That is, E can be obtained by adjoining the coefficients of some monic factor of fx to k. अब ये बाद वाली लाइन थोड़ा काम की है बिकॉज इसमें ये ई से आई मीन अलग है. So we started with the arbitrary subfield E in between F and K, and finally we proved that ये जो subfield है E that can be obtained by adjoining the coefficients of some monic factor of fx to k. और fx क्या है, mmp है थीटा का k के ऊपर, तो fx अभी इंडिपेंडेंट है E से. इज दैट फाइन?
Yes.
तो so I mean on the other side अगर I mean, you consider suppose the converse. अभी क्या किया था मैंने? I started with a subfield, and then with that subfield I obtained a monic factor of fx जिसके coefficients को मैं k पे adjoin करता हूँ, I will get e, right? Conversely अगर मैं कोई monic factor लूँ fx का, उसके coefficients को k पे adjoin कर दूँ, I will get a field in between f and k. Naturally, is that fine?
Yes.
तो और ये जो करस्पॉन्डेंस है ये 1 to 1 का करस्पॉन्डेंस हो जाएगा. इज दैट नॉट? कन्वर्सली if we adjoin coefficients of any monic factor of fx to k, we get a subfield in between f and k. So I am leaving as an exercise to you to verify that ये जो करस्पॉन्डेंस, दैट मीन्स आपको अभी एक करस्पॉन्डेंस मिल गई. अगर आपके पास कोई एफ एक्स का कोई मॉनिक फैक्टर है तो आपके पास एक फील्ड आ गया इन बिटवीन एफ एंड के. और अगर आपके पास कोई फील्ड है इन बिटवीन एफ एंड के तो आपके पास एक मॉनिक फैक्टर आ गया. इज इट फाइन? तो show that the correspondence between subfields of f containing k and the monic factors of fx is 1 to 1. ठीक है, तो मुझे दिखाना क्या है? देर आई मीन देर आर ओनली फाइनाइटली मेनी सब फील्ड्स इन बिटवीन एफ एंड के. तो अगर ये करस्पॉन्डेंस 1 टू 1 हो गया तो दैट मीन्स के जितना मॉनिक फैक्टर्स होगा एफ एक्स का उतना ही सब फील्ड्स होगा. इज दैट फाइन?
Yes, sir.
तो नाउ द क्वेश्चन इज के हाउ मेनी मॉनिक फैक्टर्स यू हैव. सपोज यू हैव द डिग्री ऑफ एफ एक्स इज n. तो नेचुरली इनफाइनाइट तो नहीं हो सकता है, राइट? कैन यू काउंट how many factors can this polynomial have? Yes, you can count. Very easy. डिग्री है n. सपोज के किसी न किसी एक्सटेंशन में इसके n रूट होंगे. एट द मोस्ट इट विल हैव अपर बाउंड, राइट? इट विल हैव n रूट्स. तो दैट मीन्स ये जो एफ एक्स है इसको किसी एक्सटेंशन में आप लिख पाओगे x माइनस अल्फा वन, x माइनस अल्फा टू, x माइनस अल्फा n. कैन यू सी द फैक्टर्स नाउ? कितने फैक्टर्स हो सकते हैं? कैन यू काउंट द फैक्टर्स नाउ?
Almost 10.
नो, एब्सोल्युटली नॉट. इनके दो का भी प्रोडक्ट हो सकता है. यू कैन एक्स माइनस अल्फा वन, एक्स माइनस अल्फा टू, इट इज ऑल्सो वन फैक्टर. एक्स माइनस अल्फा वन, एक्स माइनस अल्फा टू, एक्स माइनस अल्फा थ्री, इट इज ऑल्सो वन फैक्टर. आर यू गेटिंग?
Yes, sir.
तो कैन यू नाउ गिव मी? ये तो परमिटेशन कॉम्बिनेशन का सवाल हो गया. इट्स अ क्वेश्चन ऑफ परमिटेशन कॉम्बिनेशन. ठीक है, तो कैन यू काउंट नाउ? भाई हर एक के लिए आपके पास कोई फैक्टर है तो एक्स माइनस अल्फा वन उसमें हो भी सकता है, नहीं भी हो सकता है. ऐसे हर एक के लिए दो पॉसिबिलिटीज हैं. टू टू द पावर एन. इज दैट फाइन?
Yes, sir.
So as the polynomial can have at most 2 to the power n factors, or what I should say monic factors. So there are only 2 to the power n subfields of at most. This is at most upper bound E containing के. तो मुझे तो वैसे भी फाइनाइट ही चाहिए. So conversely, suppose that there are only finitely many subfields in between E and K. So because the extension is given to you finite, right? So there will be finitely many generators of f over k. I mean the point is f can be obtained by adjoining finitely many elements to k. The extension is finite, so suppose v1 v2 vn is the basis, तो ये basis के element को आप k पे adjoin कर दोगे, you will get f. Is that fine?
Yes, sir.
So let's say f is, suppose k may be alpha 1 alpha 2 alpha n, और ये finitely many elements होंगे because extension is finite extension. So what I want enough to prove the result, because what I'm looking for, I want to find a primitive element, right? I want to replace all these alpha 1 alpha 2 alpha n by a single element. So what I want to show that it is enough to prove the result by assuming n equals 2, because once the result is true for two elements, then it will be true for any finite number of elements by repeated application of the case n equals 2. I mean what I want, suppose the result is true for n equals 2. That means suppose a result is true for n equals 2. That means f equals k alpha 1 alpha 2. This means कि आप इसको replace कर पाओगे k, let's call it alpha 1 dash से. ठीक है. Now you want to prove for n elements, right? तो पहले तीन एलिमेंट को करते हैं, तो f को हटा देते हैं. देन so k alpha 1 alpha 2 alpha 3, this is same as k alpha 1 dash alpha 3, and again by repeated application of the case n equals 2, this will be k alpha 1 2. ठीक है, ऐसा कोई एलिमेंट मिलेगा आपको, राइट? एंड कीप डूइंग दिस, इवेंचुअली आपको ये अल्फा 1 अल्फा 2 अल्फा एन पे भी मिल जाएगा. इज दिस ऑल राइट टू यू? Yes. So note that it is enough to prove the result by assuming n equals 2. We will show the we will prove the result for this n equals 2. So assume that f is k alpha 1 alpha 2. All right. So what may happen in the first case, and the field may be finite, right? I mean, K is finite field. So this is K is a finite field. All right. K finite है तो F भी finite होगा. Is that fine? Degree of F over K is finite. K is a finite field. तो degree of F over K की मान लो कुछ है n. तो then F will be isomorphic to K power n as a vector space. So that means number of element तो finite हो ही जाएंगे F में. Is that fine? Then F is a finite field, and this would mean F star finite field है, तो you already know that the non-zero elements in a finite field forms a multiplicative cyclic group. So F star is cyclic group, is a multiplicative cyclic group. So you will have a generator. Let's call it generator है कुछ what you want to call gamma. तो ये gamma will be the primitive element. Is that fine? ठीक है, because gamma is in F, K in F, so your K gamma will be in F. On the other side, every element, non-zero element in F is a power of gamma, so F will be contained in K gamma. So F equals K gamma. So when K is a finite field, this is fairly easy. You consider the generator of the cyclic group, multiplicative cyclic group, that will be the primitive element. Now suppose it is not finite, is an infinite field. That means के number of elements finite नहीं है, infinite है. Countable, uncountable doesn't matter. Okay. So fine. What you do? You consider the subfields. In fact, a class of subfields. Family of subfields. एलिमेंट लिया है हमने अल्फा वन अल्फा टू. ऑल राइट. तो अल्फा वन प्लस सी अल्फा टू फॉर ऑल सी इन के. ठीक है. तो नेचुरली अल्फा वन प्लस सी अल्फा टू कहाँ पर है? एफ के अंदर है, बिकॉज अल्फा वन अल्फा टू आर कमिंग फ्रॉम एफ, सी इज कमिंग फ्रॉम के. तो ये जो एलिमेंट है ये एफ के अंदर है. तो दैट मीन्स ये जो सब फील्ड है ये एफ के अंदर है और के को कंटेन करता है. सो इट इज अ फैमिली ऑफ सब फील्ड्स इन बिटवीन एफ एंड के. इज दैट फाइन? This it's a family of subfields as above is a family of subfields of F containing K. that means in between f and k. But assumption ये है कि there are only finitely many subfields और k infinite field है. k है infinite field, that means कि ये जो c है infinitely many c होंगे आपके पास, infinitely many c होंगे, लेकिन सबफील्ड्स आपको फाइनाइट ही दे रहे हैं. तो क्या होगा? After some time the subfield will start repeating. Is that fine?
Yes, sir.
So as above is a subfield of f containing k and k is infinite. तो होगा क्या कि अल्फा वन प्लस सी अल्फा टू, दिस विल बी इक्वल टू, क्योंकि सब फील्ड रिपीट करेंगे तो दिस विल बी अल्फा वन प्लस लेट्स से डी अल्फा टू, एंड दिस इज फॉर सम डी नॉट इक्वल सी, बोथ आर इन के. यही होगा, राइट? सो दिस मीन्स व्हाट कि look at this element alpha 1 plus c alpha 2, ये इस फील्ड के अंदर है, दिस फील्ड इक्वल्स टू दिस फील्ड, तो दैट मीन्स alpha 1 plus c alpha 2 belongs to k alpha 1 plus d alpha 2, और इसके अंदर alpha 1 plus d alpha 2 पहले से है, इन दोनों का डिफरेंस भी होगा. ठीक है, तो दैट मीन्स कि अभी आपके पास आ गया c minus d alpha 2 will be here alpha 1 plus d alpha 2, which is exactly same as alpha 1 plus c alpha 2. Okay, but then where is c in k, where is d in k, or c minus d is a non-zero element, so c minus d is a non-zero element in k, so you can apply its multiplicative inverse to conclude that alpha 2 belongs to k alpha 1 plus c alpha 2. अब अल्फा 2 इसके अंदर आ गया तो इमीडिएटली यू कैन कंक्लूड कि अल्फा 1 भी आ जाएगा. अल्फा 1 अल्फा 2 दोनों आ गए तो फिर के अल्फा 1 अल्फा 2 भी आ जाएगा. और रिवर्स इंक्लूजन आपके पास है ही. सो दस so this proves the result for n equals 2, and once it is true for n equals 2, it will be true for any number, any finite number by successive application. Is this all right?
Yes,
Yes.
sir.
Okay, so as an immediate corollary to this, if F is a finite separable extension of K. Then F has a primitive element over K. So that means finite separable, it's simple. That is, F has a primitive element over K. So simply, I mean, every finite separable extension is simple extension. So F is a finite extension. You may assume, let's say, what you want to call alpha 1, alpha 2, alpha n basis of F over K. Then what you already know, you adjoin all these elements to K, you will get F. And let's say Pix MMP of alpha I over K, and this is for all I. Alright. And then you consider Fx to be the product. See, one thing I think we have already discussed earlier as well. कि no two irreducible polynomials have the same root. Yes, please confirm. Any one of you? I think while discussing Galois theory of equations, we have discussed this. क्योंकि वहां पे भी यही सेम टेक्निक यूज की थी हमने. Can any one of you able to recall? Yes? नहीं. I think ये तो एक्सरसाइज भी दिया होगा आपको. Am I audible?
Yes, sir.
Can you able to recall या नहीं याद कर पा रहे हो? कोई बात नहीं, चलो हम लोग वापस देखते हैं लेक्चर में. गलवा थ्योरी ऑफ इक्वेशंस. कैन यू टेल मी कौन से लेक्चर में था ये गलवा थ्योरी ऑफ इक्वेशन? कब शुरू किया था हमने? इसके बाद में होगा. This is not. Maybe this. I think और पहले होगा. चलो आप लोग चेक कर लेना, ठीक है? So is this all right or you want some argument for this? फिर से दे देता हूँ आपको. No two irreducible polynomials over K have the same root, have any root in common. That means कि P1x अगर P2x both are irreducible तो P1x के जो भी रूट है उनमें से कोई भी फिर P2 का नहीं हो सकता, P3 का भी नहीं हो सकता, Pn का भी नहीं हो सकता है, राइट? इसको जरा आर्ग्यूमेंट लिखना है इसके लिए. इट्स क्वाइट सिंपल. ठीक है.
Yes, sir.
So all these PIX basically what they are, the MMP है, or you are working over a separable extension. F is a separable. So all these elements are separable elements. Separable elements हैं. So PIX or MMP. So they all are separable polynomials. Is separable. This is for all I, as F over K is a separable extension. ठीक है. तो प्रोडक्ट भी सेपरेबल पॉलिनोमियल्स का सेपरेबल ही होगा, राइट. And this would mean fx is a separable polynomial. क्योंकि और सारे के सारे पीआईज के डिस्टिंक्ट रूट हैं और कोई रूट किसी में कॉमन नहीं है, तो प्रोडक्ट भी सेपरेबल ही हो गया, राइट. तो इफ यू कंसीडर ई टू बी द मिनिमल स्प्लिटिंग फील्ड ऑफ fx over k, तो E is a normal and separable. Normal because minimal splitting field है, separable because minimal splitting field separable polynomial का है. So then E over K is normal and separable. And hence a Galois extension. अब Galois extension है तो there is one-to-one correspondence between subfields of E containing K and the subgroups of Galois group, right. So that means के there are finitely many subfields in between E and K. और F कहाँ पर है? F E और K के बीच में, कि अल्फा वन अल्फा टू अल्फा एन. As K contained in F contained in E, there are only, we conclude that finitely many subfields in between F and K as well. And that means F is simple extension by previous result. If you have any doubt from today's lecture, anything from today's lecture, you can ask me now.